Okay, so let's look at another example of kind of an axial problem. This one's not as uniform as others. So we've got this stainless steel rod that has this kind of base section on it, with a little ledge here. So again, the main section of the rod here is 20 millimeters in diameter. And then, it's kind of got this cutout here, so it's a little ledge. And then this section of the base, it varies in diameter from 80 down to 40, between 0 and 300 millimeters. And then this section here is 600 millimeters long. Working with stainless steel here. And the question I'm going to ask is, if we apply a force, a load of some sort on the ledge, that's 200 kilonewtons, applying it kind of this direction. So, put some sort of I don't know, a collar or something around it, and apply the force to that collar. How much does that ledge move? So just drawing a quick free body diagram here. So we're going to have the load applied here, the 200 kilonewtons. And then we're going to have some sort of reactions at the supports. So again, this thing is fixed between these two walls. I'm going to assume that they're rigid, not moving, so on and so forth. And so we're going to have a reaction at C and a reaction here at A. So what we're going to want to do is we're going to use the force method. So the compatibility condition that we're working with here is that the total displacement of the rod needs to be 0. So total, it's not stretching at all. It's still staying within the walls. So we can break this up into two different loading conditions. For the first one, we're removing the support at A, so that goes away, which leaves us kind of just with the support at C here. So if we're keeping this fixed here and we're pushing on this here, then this portion here doesn't get loaded. There's no stress within that section, so the only stress that we see is caused within this section. So that portion there is stretched based upon the load, the length, the cross-sectional area, and the stiffness of the material. So taking our values, plugging everything in, we end up getting 1.9. And then again, units is important. You want to be able to figure out how to cancel these out, even if you don't necessarily, even if you're not necessarily throwing in stuff that cancels out easily. But right now, we've got kilonewton millimeters per millimeter squared GPA. So the kilonewtons per millimeter squared. Again, if a newton per millimeter squared is an MPa, then a kilonewton per millimeter squared is a GPa. So we've got GPA here, and we've got GPA here. Those two cancel out, which leaves us with 1.9 millimeters. And then, so that's that loading condition. The next loading condition would be so removing the load and then adding in the reaction from at A there. So if we treat that as an additional load, essentially, then we're going to get AX and AX on either side. So we're going to get a total amount of stretching or compression in this case that is equal to the combination of how much this part gets squeezed and how much this part gets squeezed. So the squeezing, the compression between BC is the easiest to determine. So that is just going to be equal to our load. Again, that's negative because it's a compression times the length divided by the area and the stiffness. So that gives us the stretching in terms of AX, so in terms of this reaction here. And then that ends up being kind of once you for units here, we're keeping AX. Obviously, that'll end up being newtons or kilonewtons or what have you at the end. But millimeters per GPa times millimeters squared. So again, kind of if a GPa is a kilonewton per millimeter, then GPa times millimeters squared is a kilonewton. So we end up with millimeters per kilonewton is our displacement here. Millimeters per kilonewton times whatever AX ends up being. And then we got the other section here. We got this section here with this varying cross section. We can't just. The problem is, of course, so we got the varying cross section, so we got varying areas, which means we have varying stress. So basically, what we're going to need to do is we're going to need to figure out not what's happening at the overall. We're gonna need to break this sucker up into tiny little sections and integrate. So our d delta here is going to be equal to, again, negative ax times, instead of multiplying by length, we're multiplying by a tiny little sliver of the length, dz, divided by our cross-sectional area, which in this case is a function of z, and that's just taking this thing here and dividing by 2. I kept it in the fraction notation, just so when I went to go solve it, I could plug it into Wolfram Alpha easier. Yeah, got that, and then of course our stiffness. So we can factor out AX, we can factor out the pi, we can factor out the GPA, so that gives us our total, and then integrate. So our total displacement is going to be that times the integral of 1 over our 40 minus 2 over 30 z squared dz. So again, the nice folk at Wolfram Alpha were able to tell me exactly what that was. So that'll be negative 225 over z minus 600. So that's what we got here, and then evaluated from between 0 and 300. So that ends up, when that's evaluated, that actually ends up being 3/8. So again, minus AX and all that jazz times 3/8. Kept the minus sign up front, but that minus sign is from this term here, not from the not from the integral. So we got that, and yeah, plugging everything in, we were able to get this value again keeping it in millimeters per kilonewton. And then we know that, and then we can kind of go back to our compatibility condition. We've got the total displacement in the with just the load and not having the reaction at A, plus the displacement with just the reaction at A is equal to 0. So that's going to be equal to 1.9 millimeters minus this, So that's the combination of the displacements from the base section and the longer rod section. Obviously, the longer rod section is stretching more. Is being compressed more because it's both skinnier, so per unit load it's going to be stretching more, and it's also longer. So so able to solve relatively simply for AX 1.9 millimeters divided by 0.01015 millimeters per kilonewton, which gives us 187.25 kilonewtons. So that'll be, again, based upon how we drew this initially, that'll be a load pushing that way. And then we can solve for what the reaction is at C here, just using a quick equilibrium condition for our Fx. It gives us sum of the forces in the next direction is 0, so 0 is equal to our Cx minus the 200 plus the 187.25, which gives us 12.75 kilonewtons. So we know that essentially when we take this sucker and we load it up, the stress in this section here is going to be caused by the strain induced. It's going to be a function of the strain induced. So we can find out how much this ledge moves just by finding out how much this thing would stretch based upon the loading condition just of the 12.75 and the 12.75 of just that section. So got that here. Again, load, length, area, stiffness, our kilonewtons per millimeter squared, and our GPa cancel out once again. So we're given 0.1218 millimeters. That's going to be how much our point of application of the force is going to shift when we apply that load. And yeah, that is about that.